Hello, Mr. Betts here. I want to take a look at a couple examples where we're using Euler's method to approximate the value of a function given an initial condition for the function and a differential equation. So with Euler's method, essentially what we're doing is we're taking into account the slope of the function and we're moving along the x-axis and figuring out what the change in the y values are going to be for a certain number of steps. So we're going to organize our work with Euler's method using a chart. And so the chart is going to have four columns here. So the first two columns are just the x value and the y value of the function. Then we're going to take into account the derivative at the point. So at whatever point the x and the y values are, we want to figure out what the derivative is. And then based on that derivative, we're going to find a change in y that is going to approximate the value of the function at another point. So in this particular example, we are starting at the point 1, 2. So the x value is 1 and the y value is 2. And using the differential equation that's given to us right here, we can find dy dx at that point. So that's going to be 1 times 2 minus 2. So that's actually 0 here. And so the change in y, if you remember linearization, basically takes into account that the derivative or the slope of the tangent line is going to approximate the slope of the secant line. And so delta y is going to be approximately equal to delta x times dy dx. And so since the change in y here is 0, that's going to be 0 times delta x. Now, since it's 0 times something, we know it's going to be 0, but delta x is going to be given by a formula that we've seen before, b minus a over n. So b is the ending value, the ending x value, which is 2, minus the starting x value, which is 1, divided by the number of steps, which is 2. So delta x is going to be 1/2. So the change in y for our first step here is going to be 0 times 1/2, which is 0. So the change in y tells us how much y changes from one point to the next. So going from 2 to the next point, it's going to change by 0. So y is going to be 2 for the next point. Delta x, the 1/2 right here, tells us the x value is going to increase by 1/2. So the x value at the next point is going to be 1 plus 1/2, or 3/2. Then we use our dy dx formula, so the differential equation that's given to us to find the derivative at that point. So 2 times 3/2 minus 2 is going to be 3 minus 2, which is 1. The change in y is going to be 1 times 1/2, which is 1/2. So the next point, we're going to increase by delta x for our x coordinate, which is going to be 2. We're going to increase by delta y, which is 1/2. That's what we just found right here. So it's going to be 5/2 or 2.5 or 2.5, however you want to think about that. And we're actually done because we are at the x coordinate of the point that we're trying to approximate right here. So what this is telling us is that when x is 2, y is going to be approximately 5/2. So one important thing to keep in mind is that the y values that we're getting right here from delta y in this column are going to be approximations. Those are essentially linear approximations. So that tells us that when x is 2, y is going to be approximately 5/2 or 2.5 or 2.5, however you want to write that. Okay, so in the second example, we're actually given the same information, the same differential equation, the same initial condition. We're approximating the same value of the function, but this time we're using 4 steps instead of 2. So we're, in theory, getting a more accurate approximation because we're using smaller steps, and each step is going to have a smaller error, so we should get a better approximation. So we're still going to have a chart that looks the same. So we're going to have x and y values. We're going to have the derivative, and we're going to have a change in y that's approximated by the derivative multiplied by delta x. So first thing I'm going to do here is find delta x. Delta x is going to be b minus a over n, which will give us 1/4. And so starting at the point 1, 2, we find the derivative at that point by plugging it into the differential equation. That's going to give us a derivative of 0 at that point. So delta y is going to be 0 times 1/4, which is 0. So y is going to change by 0, x is going to change by 1/4. And so essentially what we do is we add those two values to the x and the y to get our new x and y. So x now is going to be 5/4, y is still going to be 2. Now dy dx at that point is going to be 2 times 5/4 minus 2. So that's going to be 5/2 minus 2, which is 1/2. Then delta y is going to be 1/2 times 1/4, which is 1/8. And so again, we increase x by delta x. We increase y by delta y. So we're going to have 6/4 or 3/2. Y is going to be 2 plus 1/8, which would be 17/8. And we find dy dx then at that point. So that'll be 2 times 3/2 minus 17/8. So that's 3 minus 17/8, which is 7/8. So delta y then is going to be 7/8 times 1/4, which would be 7/32. So now we're going to add on delta x again, which would be 7/4. We're going to add on delta y. So 17/8 plus 7/32 is going to be 68 30-seconds plus 7/32, so 75 30-seconds. And we find dy dx at that point. So that's going to be 2 times 7/4 minus 75 over 32. So we get, what is that, 14/4 over 4. So 14 over 4 minus 75 over 32 will be, multiply that by 8, we get 112 30-seconds minus 75 30-seconds. So 37 30-seconds. That's our dy dx value, times delta x times 1/4 is going to give us 37 over 128. The arithmetic here is getting a little bit beyond what you would probably be expected to do on an assessment without a calculator, but we are getting close to the end here. So we add on delta x again, and we're at our final x value, which is 2. Our y value, we're going to take 75 30-seconds plus 37 1/28. So that's going to be 300 1/28 plus 37, which would be 337 over 128. And that's actually our final answer. Now, we don't want to just stop and say we're done, but this right here tells us that f of 2 is going to be approximately 337 over 128. This is a little bit more complicated than, like I said, you would be expected to be able to do without a calculator. However, I just wanted to show you that using more steps is going to give us a more accurate approximation, which we don't know what the value of the function is at 2, but you can see that we're getting probably a more precise answer because we are taking more steps and our error along each step is going to be smaller.